Okay, hello everyone, and welcome to our introduction to Neural MT at LILT. My name is Carmen, and in the next 20 minutes or so, I'd like to give you a high-level introduction into Neural MT and share some results and why we've launched Neural MT and why this might matter for you as a translator or as a business. If you have any questions, you can use the Q&A section in this application, and I will answer them at the end of this presentation. All right, let me just go to present. So this webinar will consist of two main parts. First, I will provide a brief introduction to LILT's adaptive neural technology, which combines live human feedback with machine intelligence in a continuous cycle. And I will also give a general introduction into neural machine translation. And second, we'll go through specific examples and case studies to see what the quality of Neural MT is like, whether it's really that good, like other people say, and also what other advantages it brings and what this means specifically for you. Just a note, this is not a presentation that deep dives into the mathematical or algorithmical aspects of Neural MT or neural networks or how to train them. It will rather be an overview on how it works, to understand it on a high level, and also understand the implications for translators and businesses using LILT's neural machine translation technology. All right, so neural machine translation has been deployed by several other MT providers and enterprises. And what's special about our implementation? So those of you who are already familiar with LILT and our platform know that LILT implements a human-machine partnership with a real-time feedback loop. And this is what you see here in this image. So LILT is in fact the very first translation engine that utilizes this continual human-machine feedback loop, first with the old machine translation architecture and now also with neural machine translation. So what is this real-time feedback loop? This real-time feedback loop means that human translators, this is what you see here on the left-hand side, represented by this guy with the laptop, these human translators produce higher quality translations at much higher speeds through receiving predictive suggestions from an intelligent machine. This is what you see here on the right-hand side. And so this machine, which is now a neural machine translation system, continuously learns and adapts from human feedback, which in turn produces even better suggestions back to the human over time. And this is how a virtuous cycle is created. So this is exactly this feedback loop that I was talking about. All right, so that's a very brief overview of LILT's core technology. Now let's step back a little and look at how Neural MT works. And for this, I'd like to go a little bit over the history of machine translation. So machine translation has been around for a while and evolved over the years. And different technologies were introduced that resulted in breakthroughs. And so first people were developing rules. So here linguists were sitting down and actually writing rules to teach the system how to translate from one language into another. Then at some point, statistical work-based models were introduced where the system learned on its own which words are translations from each other, so new incoming words could be translated automatically. Then this was eventually extended by statistical phrase-based machine translation. So here more context could go into the translation. So it wasn't really, wasn't anymore just a word-by-word translation, but entire phrases could be translated. And then finally, recently neural machine translation was developed, and this is what we will talk about in the following slides. So let's look at two key ideas in neural machine translation that ultimately allowed for better quality translations. So the first idea is about word embedding. So statistical machine translation uses symbolic representations of words. And this means if words are written differently, then they are also different for the system, and it cannot connect words that are actually related. So it does not understand the semantics of a word. Like here, this example, car is not the same as cars, because here there's this extra S. So for the statistical system, these are two different words, and it doesn't know that one is the plural of the other, that they're somehow related. And NeuralMT uses distributed representations, which are also called word embeddings. And this means words are encoded as vectors in a multidimensional space. And in the space, similar words are close to each other. So there's some kind of semantic representation of these words, and words that are similar, that have a similar meaning, that they are close to each other in this space. You can even perform operations on these words or on these vectors, which you see here, for example. So this is a very classic example. So this is about how words are represented. Then the second is about context. So in statistical MT, when producing translations, it uses only a limited context. So often the last 4 target words, or sometimes it's less, sometimes it's more, but the context is very limited. And in NeuralMT, instead, it uses the full source and target sentence to produce a translation. So with this, it captures more meaning during the translation process. And of course, then it can generate better translations. All right, so let's look at this in more detail. So neural machine translation implements this encoder-decoder architecture. So the process of translation involves these 2 components, an encoder and a decoder, and it starts here at the bottom. So an encoder turns a sequence of words into a set of representations or sentence embeddings. So if we go back to this previous slide, we talked about word embeddings. These are distributed representations of words. And if you extend that from words to sentences, you get sentence embeddings. We're going to see an example also in the next slide. So the encoder, again, turns a sequence of words into a set of representations. And then this is here, this, and then the decoder generates from this sequence, from this embedding, generates a sequence of words based on this embedding. And this idea of an encoder-decoder architecture is the basic principle behind neural machine translation. So in fact, this is also the type of architecture that is at the core of deep learning, and where the biggest emphasis is on learning good representation. So this part here is essential. So what does this look like in detail? Let's look at the encoder. As I said, the encoder turns a sequence of words into a vector. And you can see here some example of learned sentence representations. So they're here projected into a 2-dimensional space so that I can actually show them. Otherwise, or in reality, they're in an n-dimensional space, so many more dimensions. So the phrases or sentences, they are clustered by meaning. You see here that we have 2 clusters here. You also note that both clusters have similar internal structures. So if you look at these sentences, here in this left cluster, they have a very similar structure, and here on the right-hand side, they also have a very similar sentence structure. And within these clusters, also similar sentences are close together in the vector space. So here, for example, Mary admires John, or Mary's in love with John. They are close together, while you have here this inverted, John admires Mary, John is in love with Mary. So these are, so each of these pairs, they're close to each other, but they are further apart from each other. So the figure, this figure clearly also shows that the representations are sensitive to the order of words. So this is again the example that I just explained here. Here the order of words is very similar. Here the order is a little bit different, so they're farther apart. And it's In general, it's a little less, or it's more insensitive to replacement of, for example, active voice and passive voice. But so just overall, to summarize, the encoder takes care of encoding or representing sentences into a sentence embedding, and then you find them in this vector space. And as I said, sentences that have a similar meaning, they're close to each other, and sentences that have very different meaning, they are far apart. Okay. And so what does the decoder do then? The decoder predicts translation one word at a time. So if we have here a given source sentence, she gave me a card in the garden, then this is in a sentence embedding represented. And then we basically predict one word at a time. So here in this example, the system already predicted 4 words. And then based on this entire source sentence and on these already predicted words, it predicts the next word. And the next word here in this case would be Garten in German, which would then come here as the next word in this translation suggestion. All right. So this technology of actually this architecture with the decoder predicting one word at a time, this also matches very well with Lil's interactive MT technology. If you've worked with Lil before, in which a human translator produces a translation of a sentence in collaboration with the MT model, and you do that one word at a time. So until then, eventually the system produces until you and the translator and the system produce an entire sentence. All right, so now let's pause a little bit. I've spent some time talking through how Neural MT works, but why did we launch Neural MT, and what does this mean specifically for you? Let's go over some specific data and results from our experiments that we did also with some of our customers. So here are examples of evaluations that we did across 5 different domains. So this graph basically shows 2 results. The first is that Neural MT quality is better than statistical MT in these 5 domains, or in these 5 tests. This is basically if you compare these purple bars against these gray bars. So the gray bars are the old statistical system, and the neural bars are these purple bars. And you see that these purple bars, we only have this comparison here available for the first 3 domains. The purple bars are higher than the gray bars. So this means that the quality of the neural machine translation is better than the statistical system. So this is both without adaptation. Now the second result that this graph here shows is that adaptation significantly improves quality. So by adaptation, I mean this, what I showed you earlier, this real-time feedback loop. You can adapt the system either by uploading translation memories or by translating within the LIT application and collecting more translation memories and then training the system in real time. And you see that these bars for Neural MT with adaptation, they are much higher than the ones without adaptation. So yeah, many of you probably already know that adaptation is good for MT quality, and this has been shown also for statistical MT many times. What I want to show you here is with Neural MT, adaptation is much more effective. So if you compare here on the left side, you see the statistical system, the baseline, and then the performance, the relative improvement that you get with adaptation, so adapting the statistical system. And then here on the right, you see the neural system, again, the baseline, and then relative improvement with adaptation. And you see that, so this is all starting with the same baseline data, and then with the same adaptation data, which was here in financial domain. And you see that here for the statistical, we get about 50% of improvement, and for with neural, you get basically more than double the improvement. or more than double the quality. So this means that with neural MT, adaptation is significantly more effective than with statistical MT. Okay, so far we've seen only automatic evaluation results. These were these two graphs before, but what about having humans evaluate the translation quality? What you see here is the result of a case study we did with one of our customers, Zendesk. We translated samples of their support content with the adapted statistical system and the adapted neural system, and then let them decide which one is better. And these are the results that you see here. Most of the time, so 71%, if you add these two here on the right, neural was better or equal quality than the statistical system. There are still cases where the statistical system is better. So here, the 29%. This is also in line with what others report. But in general, neural MT is better. So this is what we wanted to show here. And I also wanted to show you an example sentence here. So this is for English to German. So we have this English source sentence, here the statistical machine translation output, and here the neural machine translation output. And if we look specifically at some of the issues that are here in the statistical system, that the neural system gets much better. And this is specifically around verbs. So here verb is missing in the statistical MT output, which is there in the neural MT output. Then also gender agreement. So the German word for organization requires Z, and here in the statistical system it was producing S. And then also the order in the ordering of words within the sentence is much better arranged here with the neural MT. So actually the neural MT output here is perfect. All right, so this is about quality. So we've talked about the implications of neural MT on translation quality. Now let's look at some technical advantages that it has as well. So this chart shows the English to German model sizes. So you see here on the left side the statistical model, which requires a translation model and a language model. Especially the language model requires or is very, very large. And then for comparison here, you have the neural model, which is much, much smaller. And so this means, so just to give about a size of what the difference here is. So this is, we're talking here about a magnitude of 400 times and more smaller. And what does this actually mean, or what does this enable? So we can faster deploy new languages. Then also we are able to deploy or use an auto-scalable architecture. And finally, also we automatically and seamlessly convert our old systems to the new systems. So you don't need to re-upload translation memories and so on. Okay, so yeah, while NeuralMT requires more compute power, we were still able to integrate it with only little loss in performance, which I mean here in speed, in the interactive setting. So this animation is taken from our application. So and it's showing you how you interact with the system, and you see how the translations here are adjusted in real time. And this is basically instantly. And so we don't have any big latencies just by using NeuralMT. Okay, so just to summarize, we integrated neural machine translation in a way that you still get the same benefits from our integrated architecture. So this means NeuralMT is still tightly integrated with translation memory and term-based, and also can be centralized, so if you're working in teams. It's adaptive and interactive, and we have this integrated in our cloud-based CAD editor, and it can be accessed via web app and API, so we have full API integration. So finally, I'd just like to share a few plans with you that we have regarding neural MT. So far we deployed only German and Chinese. So obviously we want to launch more language pairs. So for this, we want to convert the existing statistical systems to neural systems and also add new language pairs. Then at the moment, we've made Neural MT available for business customers. So we want to give access to Neural MT to all our users. So this means a full rollout. And the last thing, we also, so lots of research is happening in academia. And with our research team, we are continuously investing in research and development and rapidly improving the neural MT architecture and quality. All right, so this is all I wanted to share with you. Now, are there any questions? Okay, there are no questions. Then I'd like to thank you for joining this session. And as I said, please let us know if you have any questions later or if you would like to see a demo. Thank you. Bye.